Good morning, everyone. I warmly welcome all of you to today's webinar on analysis of tall buildings as per IS16700 in ETABS. As the demand for tall and more complex structures continues to grow, engineers must adopt advanced analysis and design tools that ensure safety, efficiency, and compliance with the latest standards. ETABS is one of the most widely used structural analysis and design software packages for high-rise buildings, offering powerful capabilities of modeling, analysis, and performance evaluation. So in this session, we will explore the fundamentals of ETABS, understanding its workflow for tall building projects, and discuss how the provisions of IS 16700 can be incorporated into the analysis and design process. I hope this webinar will provide valuable insights into modern tall building analysis and code-based design approaches. Thank you for joining us, and let's begin. The objectives for today's webinar is to introduce you to various features and tools available in ETABS for the tall building analysis, starting from modeling, analysis related, and we also cover design and our recommendations along the way. With an example. So we'll start with the definitions and modeling, where the modeling of the building shall follow a simple approach. So that reflects the distribution of mass and stiffness properly for all significant internal forces under seismic actions and deformation shapes. So we have several definitions. I believe most of you are experienced in using the ETABS program to an extent that these features, definitions for the materials, section properties, loadings, etc. are already well known to you. So I will skip some of those. But just for the introduction's sake, I'm pointing out all of this. So we have a quick set of tools and features for these definitions, right? They're already used in several projects. Similarly, we also have drawing tools, starting from simple joint line area that can be modeled for modeling the joints for joint loads or restraint assignments, lines for beams, columns, braces, area for floor slabs and walls and foundation rafts, etc. We also have link. A link is a special element that can be used to model highly nonlinear behaving element like force deformation behaviors such as dampers, isolators, right, that can be modeled using the links. And then to study the performances or the responses in the nonlinear range, we have nonlinear hinges that can be assigned to frames and area, specifically the walls. So the moment, plastic rotation, shear, and plastic deformations, etc., can be studied in this hinge response output. So other than that, we have DXF BIM import by other Revit. Those standard supports are available in creating your model. And then specifically for this course, section 7 talks about the structural analysis, and we need to do a full 3D analysis. So our software is well capable of that. And then for the building that we are going to analyze, there are considerations related to the rigid end offsets, how to model these, and then floor diaphragm. So we have to study the floor diaphragm and then decide on its flexibility, whether it is rigid or semi-rigid as applicable. That points to 1893 code. Then the cross-sectional properties and the cracked state that is given in the code. We have to follow those. And then P delta analysis has to be performed always. And then it also gives you the load combinations to be used. Okay. So these are the primary things in your modeling. And then for the analysis, we have to prepare the model for. Other than that, we also have model related, such as stiffness related. For example, foundation flexibility, right? In plane stiffness or out of plane stiffness of slabs, when to consider, right? And the interstory drift, etc. So all of this are discussed under the 7.3. We already have all of these record features for the modeling. And then the last one in that section would be 7.4, building movements, which talks about buildings taller than 150 meters or 100 meters with mass asymmetry should be studied for long-term building movements. So that is also possible within the ETABS program. So let us assume we have created the model, the one we are seeing in the picture. And then we have to apply the loads. So the member loads to the floors and beams, you can directly apply them to these members as joint, line, and area. Load types are available. We can apply it as usual. And for the lateral loads, so wind standard IS875 is based definition is already there in the program, which can simply enable, and program will apply it as per the selected method, whether it is based on the diaphragm extents or modeled specific null areas that represents the wind resting elements or the claddings. And for the gust factor, it is not automated in the program, so we will have to calculate it externally and then apply it as a user load. So user loads will require the diaphragm modeling, which we usually do. So diaphragms can be loaded with these calculated story lateral forces. Similarly, for the seismic, we have 1893 for up to 120 meter tall. We can use the minimum base shear, design base shear, similar to that of 1893. So you can use this 1893 base load pattern, automatic lateral load for up to 120. If it is more than that, then we'll have to work out the base shear coefficients as per table number 4, and that can be assigned as user coefficients instead of the auto lateral load based on 1893. And then we also have situations where multi-towers are being modeled under a common podium. So in such situations, we use user loads to the diaphragms. So we have the option to enable multi-tower option. Once we enable it, we cannot use the standard auto code-based definition. So we'll have to use the user loads specific for individual towers. Anyway, the code is also asking you to model the individual towers as well as the combined one. And both should be done. So when the individual, you can get the forces and then apply it as user loads in the combined one for specific towers. All right. Next, all the required analysis types that are possible are required in any building analysis is available within the program. It's a powerful tool, so which can handle starting from the very basic linear static analysis, elastic analysis for the design requirements, and also perform the model of dynamic properties and the response spectrum case that can be code based or site specific. You can develop site specific and use it within the program. So we have these two primarily used for elastic analysis. And then we have the construction sequence case. Instead of modeling the entire structure and analyzing the whole structure for the analysis, the construction sequence can be specified, and then the analysis will be performed in those stages. I hope the audio is fine now. Or do you still find any echo in my audio? All right, I hope it is settled now. Okay, so construction sequence can handle elastic as well as nonlinear, time-dependent properties like age of the concrete in your sequence case. So that is possible. So it is a nonlinear case. When enabled, that is also considered. We have nonlinear static, for example, a pushover analysis, which can be used to study the response of the buildings. For example, the code is talking about the progressive collapse, section 5.8, and key element identification. And for building movements, for gravity columns, etc. So you can utilize the nonlinear static case type for this. So pushover is a lateral sway analysis, um, which can be used alternate to time history analysis, which will be computationally costly. Pushover will help you in resolving that. But I will demonstrate with an example for the pushover. Program is also capable of the time history analysis, dynamic time history analysis, considering the material nonlinearity as well as geometric nonlinearity. So even in time history analysis, it can be based on model, which is fast nonlinear analysis, or in other words, FNA in short form, or the direct integration step by step. Both are possible. So other than these, we can also get other types of outputs once the analysis is done. So the displacements, member forces. So program can comprehensively give the response plots for the lateral load analysis, story response plots. And we also have plot functions when you use a nonlinear pushover or a time history to plot the response with respect to time. And then nonlinear hinge responses. I will also demonstrate this in an example. And then energy cumulative outputs. So before entering into the modeling in the ETABS, so there is a common requirement how to get the data for wind tunnel analysis. So it is available in the tabular output show tables. You can get the mass moment of inertia from this particular table. Mass summary by diaphragm. So for this, we need to apply the rigid type of diaphragm. And then you can get the displacement of the diaphragm center or center of mass. And there will be requirement to convert the spectrum cases to linear cases, simplify things. So data extraction you can do using the story force output from the analysis results after the analysis. So you can extract this table and you can get the lateral force per story as Fx equal to story force of that current story minus the story force in the story below. That difference basically gives you the forces. Okay, so the story force output is basically cumulative, so you need to get the difference to get the individual level force. So with these two things, you'll jump to an example. I have a 30-story building, 90 meters tall, and we have provided about 3% of shear walls to take care of the lateral forces. And it is a simple configuration, but should be sufficient to discuss all the features required for this code to be implemented for your analysis. Okay, so let's so quickly in the materials I've used M40 and M30 grade concrete and Fe550 grade rebar materials. And under the section properties, so columns of 450 by 450 M40 grade till 7th story, and beyond that it will be M30. Similarly for beams, and for the floor slabs, 150 thick M30 grade is used throughout. And as you can see the configuration, I skipped the modeling part. And we'll enter into the considerations that are key for this analysis, structural analysis. So clause 7.2 talks about the rigid end offsets for linear members in the joint region when centerline modeling is adopted. So centerline modeling is being adopted. And if I right click on a member, which I have already applied, but I will show you from the information and then where to find it. So end length offsets, you have rigid zone factor now kept as 1. So general recommendation would be 0.5 for RCC buildings, but since rigid end offset is required, then rigid means then it is going to be 1. 0 means flexible. So this assignment to the frames you can find under end length offsets. And you'll have the rigid zone factor. Handle this. I put 1, then program identifies the connectivity from the connected object, the column. Let's say this is 450 by 450, and then 225 on the left for this beam. So for that region, we'll specify this factor as 1. That means it is fully rigid for displacements. So this will alter your lateral displacement and mode shapes, the time periods. So that effect being assigned to the frame members. Next is for diaphragm flexibility. I'm using a semi-rigid diaphragm just for demonstrative purpose. You can also use a rigid as applicable. And then for the cracked section properties, as per table number 5, it has been given for serviceability and then strength. Although program can handle both in the same model, so for practical purposes, you can have the ULS model with these properties and then serviceability SLS model for modeling the modifiers separately for the serviceability checks. So I'm showing the model, which is for the strength design. So the assignments can be made at the definition stage of these members. For example, there is an option where you can specify the property modifiers I did not modify, but I made it as an assignment to the objects directly after modeling. Now, frame property modifiers, and you can see this assignment here. Right. So moment of inertia 0.35 of Ig for the beams. Similarly for the columns, slabs, and walls have been applied in this model. And then the fourth, P delta analysis. So this is critical point for discussion because in 1893, we don't have this prescription that what is the load factor to be used. And we generally use the 1.2 factor, which is the maximum gravity load, factor gravity load acting on the structure. So 1.2 times dead and 1.2 times of live. However, in this code, for this tall building requirement, we have to include the lateral loads. When we do this in the usual fashion, like you can see the define P delta options, currently it is turned off. We have to consider this in X direction as well as the Y direction. And it is also positive ones and negative ones. So you'll have to, you can define this directly here, but you'll have to unlock the model and run the analysis with a different set of P delta, but that is not going to help us. So the suggested way would be create P delta cases on our own. So next, let's jump to the load cases. If you could see this, the very first one is PD for P delta, X positive, and it is a nonlinear static case, which is going to define the initial P delta, like starting from zero initial condition, and can see the load factors for dead 1.2, live 0.5, and EQX 1.5. And it will have the geometric nonlinearity considered as P delta. That is the definition. So the next one is for the negative. The next one is for the positive Y, negative Y, and similarly for the wind. Right. So these are the individual or respective P delta starting cases for the lateral loads. So loads have been defined using patterns. So EQX, EQY, and wind X and wind Y. So keeping things simple, it is applied without any eccentricity. We have to apply it. So just for demonstration, I'm keeping it simple. And you can see I have calculated the time period, approximate fundamental time period from the code and used it here. Similarly, for the wind, I'm using the exposure extents from the diaphragm and applying the net pressure coefficients in the X direction and one for Y direction. Right. So in case of gust, what you'll have to do, you have to set to user loads. And then if you press modify, then it will expose the diaphragms and you can directly apply the forces per story and update this. Right. So we are not doing this. We have simple dead and live gravity loads, one seismic and one wind lateral load sets. Okay. So now Coming to the load cases, I've defined load case for the seismic, positive in x direction, negative in x direction, positive in y, negative in y. Similarly, other forces for the y. For these cases, we will start respective P delta case. Already defined that. Note this case, linear static case, will use the stiffness of the previous case, not the loads. So it is only the stiffness from the P delta and the lateral load is applied. It's the same as earlier. It is also same as what we do in the initial P delta analysis. Okay. And we have also included the response spectrum as model grids and the response spectrum in X and Y. I have skipped the vertical direction for keeping things simple. The mass source definition. All right. Now with these settings, you can perform the analysis. It will take less than a minute, maybe 30 seconds I'm expecting. It's done. So the program is super efficient in the computational efforts also. You can see took about 20 to 30 seconds to complete these number of analysis. So the discussion on the display of responses like deformed shape, etc., are the usual ones. I'm not discussing much in that. You can see mode 1, 2. Rather, I would see the model information, participating mass ratios, and you can see the structure based on the configuration. It is well behaving. You can see about 70% in the first mode itself, and it has 99% MMPR, right? So the first mode is 3.2, second mode is 3, both are translational, and third one is 2.4, far away from this, and it is torsional. So we'll have to check the flexibility of the building, uh, the interstory drift stability coefficients, which requires a small calculation. I'm not demonstrating it, but you can get the story force output as discussed for uh, the requirement for converting the spectrum to the linear static. So in the same way, you can obtain the axial force, and then the other table you can get the displacement, and you can do the computation, the theta value, and with a small quick Excel spreadsheet, you can see whether it is less than or equal to 0.2. So that can be established. For this building, it is fine. I already checked, not demonstrating. All right. So from here, the design basis would be IS456 and other criteria through the ductile and seismic through 1893 and 13920 be applicable, and you can proceed with the design. If you have any special combinations that that is required that you are introducing, then you'll have to define load combinations other than the default ones and use it in the design. So I'm skipping the discussion on the design of these members, that I would focus on more on the analysis. So this is the usual fundamental analysis and the response that we will look at after any tall building analysis. Now I'll switch to another model where I have created a construction sequence case. So I have added data and construction live, and then you have this. I'm using the auto construction case. You can use this feature to quickly build the construction sequence case for you. And then once it is enabled, then you can go to this load case and you can find it as auto sequence case. This is not editable, you can see. So you cannot update, although you can see some updates that you can provide here, but the OK button is inactivate. Right. So what you can do is you can utilize this and create a copy, add a copy of this case, and you can do the stage operations manually within this at each stage. The basic definition is at each story, structure is added. So program internally groups each story, all the objects in the story to a group, and that will be applied as story. This is taken care by the program automatically by story, and you can also add the loads as added. So dead load and construction load, and you can specify the scale factor, and then you can perform the analysis. So each stage, this is stage 1, and then we go for stage 2, 3, 4, 5, like this. So stage 3, you will see the complete 30 stages, and each will have similar set of definitions, adding a story, loading that, and then perform the analysis. So you'll get the results at each stage. So this helps you, this particular analysis type will help you in finding the vertical settlement, axial shortening. Axial shortening, if you want to consider the creep, then you can also enable the material properties are time dependent, and the material property definition needs to be specified as, let's say it's a concrete, you have the time dependent properties here, and you have to enable those time dependence, whether it is creep, shrinkage, or stiffness, and you can enable them based on standards, or you can specify it as user. CEB FIP90 is commonly used. You go there and you can see the creep coefficients, and this is time. Right, this is creep coefficient, and shrinkage strain used is 0.0004. Sorry, 0.0004, 0.04%. Right, so you can modify these values as a user, and then for the creep analysis, so the reinforcement required for the vertical members will be utilized directly from the design. So you'll have to run the analysis for the linear static and perform the design, and then enable this to study the long-term building movements specific for this. For now, I'm excluding the time-dependent properties and running it as a linear static, but in sequence. Right, now if we jump to deformed shape for this particular case, auto sequence, right, stage 2, stage 3, stage 10, all. You will see the variations in the settlements when it is analyzed as the whole structure as well as construction sequence stage. So today we are restricting ourselves only to demonstrate this, but um, if there are specific queries on this, we can discuss this, support. Please let us know on that. So next is for this tower, we are performing a nonlinear analysis to identify the key elements, which will help us to identify the key elements. And this is related to the progressive collapse section. So from the linear analysis, we will not have much information regarding this. So we'll have to perform a nonlinear analysis considering the material nonlinearity. And I have defined instead of a time history analysis, which is nonlinear, which will be computationally heavy, I used a pushover analysis for this. For that, we have the gravity loads and then the actual pushover case where we specify the pattern and importantly the displacement control. We'll be applying it in multiple states. I mean, results are saved in multiple states. And the displacement control, we are applying 450 mm. We are using H by 500 limit, code limit. So 90 meter and 500, we are getting 450 mm. And we are monitoring a joint at the topmost level. So we have one more pushover case, which will be similar, but the displacement monitored is for 900 mm. So loosely, we can say that is for IO state, immediate occupancy, about 0.2 to 0.5 percent of drift. And this one is about 1% drift for life safety level. And I have performed the analysis. It will take a few minutes, but we also need to apply objects. Switch to another model before this. We need to apply nonlinear hinges to the beams, columns, and walls, which can define the under the section properties, frame wall nonlinear hinges. And you can define based on the hinge type, deformation controlled or force controlled. And then we have, for example, for the beams, I go for the definition, you can define the moment rotation, right? So you can define different sets depending on the cross section and the reinforcement, etc., based on the guidelines you're following. The program also has an automate feature to apply these based on ASC41, which I have used. For example, for the beam, you'll go to the hinges. I can quickly use nonlinear beam or column and I'll set it to auto. Then it will ask for the hinge type. So predefined hinge definitions available from the tables of this code, ASC41. It's also derived from the FEMA 356 and ATC40 documents. You can directly assign this quickly. For example, beams, the degrees of freedom, which we are monitoring, M3, out of plane. and then the shear value from particular combination which is expected, and then reinforcing whether it is confirming is whether it is a ductile member, yes, then reinforcing it directly from the current ratio, right? So after the point E drops load carrying capacity. So standard set of definitions we'll make, and you can explore this and apply this to the members. Press OK and it will get applied. Similarly, for the walls, you also have wall hinge and reinforcement for wall hinge. Currently, it takes from the design. So you have to perform the design before perform this analysis, the linear static analysis. If not, you can also directly specify, take it from the specified ratio, or you can also set more complex definition of this configuration of rebars. Right? So all of this are possible. Currently, it is from the design, and you can go to the wall hinge and quickly assign a auto fiber PM3 hinge, or you can go for a more general one and apply vertical, horizontal, and shear. Right. So once these are applied, I'm switching back to the original model where these have been applied, and I applied this for the lower stories where the hinges are expected to reduce the computational efforts required here. So I will show quickly. You can see for the beams and columns, right click on a beam. So it is loaded with these hinges at these locations, automatically picked up from those settings. And the hinge, you can see auto M3 hinge has been applied for the beams, and for the columns, so P, M2, and M3 hinge been applied. So once these are applied, you can go back to the section properties and review the generated props for the column, for example. Right. Minimum interaction surface. So all the required definitions are automatically generated by the program. So basically, we want to study the nonlinear response to these hinges. Similarly, we have assigned hinges for these walls. All right. So we have performed the nonlinear cases, the pushover. So the basic idea is when the structure is weighing to the maximum allowed limit of 450 mm in the first case, and second case double of it, 900 mm. Let us look at the responses. So this type of analysis is going to help you in identifying the key elements. T-form shape, push first case, We are focusing on the hinges, the displacement. Step number 0, you can go to, there are 17 steps. I'll directly go to the 17th step, try 10, and then go for. And you can see the 10th step for displacement of about 341 mm. You can see there are yielding of the beams, right? We go to 17 is 450 mm, and you can see base of the wall has just yielded. The color code, which represents BCD, is the peak points of the hinge definition, the backbone curve. You can also switch to the acceptance points as immediate occupancy or life safety. And in the other window, I will show for the second case with 900 mm, 16 steps. And you can see with 900 mm, these have been yielded, these beams specifically. If I select a member and if I go to display the hinge results, and you can see under the backbone curve, the yielding is just at the yield point, and then it has yielded and strain hardening is happening. And this is the plastic rotation, moment, plastic rotation output, right? Now there will be thousands of members, right? How will you monitor these? So we have a feature called performance checks. This is closely related to performance-based design, but you can utilize this feature to identify the key elements and all. So I'm showing this two definitions. One is for first pushover case 450 mm, and second one is for 900 mm. So definitions have been made, and then under the display, you can go for performance checks. So you can see the standard collapse prevention, life safety, and immediate occupancy levels directly in the graphical output, and it will show. Let's say if it is for immediate occupancy, which is just around the yield point, and you can see most of the members, or all the members. This is for the wall hinge, for the frame hinge, and you can see the color variations in certain members where this one, the value is 3 point. For immediate occupancy, it is yielded. So the ratio is greater than 1, and it is greater than the immediate occupancy level. And it could be within this life safety limit that you can check, or under collapse prevention, the final one to check. So most ratios are less than 1. That is, it's not into the collapse region. And this is for graphical output. And then you also have display performance check usage ratio. So this is for the whole, where you can set the limit and then see the ratios, the graph. So considering all the wall hinges, all the frame hinges together, and you'll see where these are. We can see the colors for immediate occupancy. So this is the level, and then these are exceeding. Maybe for collapse prevention, so these will be below this level, right? So basically, this gives a comprehensive uh, set of outputs required in this tall building analysis code. I will stop there, and then I will switch to one more model where we have modeled a podium with the same tower. It's closer to a real structure where there are members beyond the tower, which represents the podium. And we have introduced some more walls which take care of the lateral forces. And then some of the stories are below the grade level. 2 stories above that, it's a quite complex one. But this particular example is to show you, to study the sensitivity, which I have performed within the same model. So we'll have to change the section properties specifically for these podium level objects, the floor diaphragm and the walls for the upper bound and lower bound limits given in the table number 6. I've created 2 cases. So this I use it as a nonlinear stage construction case where it allows me to change the modifiers for this case alone. So the upper bound has been set here for the floor diaphragms and the retaining walls. And the other case is lower bound with lower bound modifiers. Where these are defined under the define named assignment sets, we have frame modifiers. So, but these are shells, so I'll go back. Shell modifiers for lower bound, I used 0.15, and this one upper bound which is 0.5. So both axial is in plane and out of plane using this. One is for the floors and one is for the walls. Right? We are using the appropriate for each case. So each case is using different stiffness modifiers for this, and the results are available in the same model. Right. Right. The response that we are looking at is the forces. See, the analysis is complete. Let me go to right. Right. And then you can study this cell forces for the backstay sensitivity upper bound. We can see the forces, and this one, the other window, I will show the lower bound value. You can see the difference. So I'm studying the in-plane forces coming to these backstay members. You can see the values are between, so close to this wall, 400, and here a little lower, it's around 300, right? And the forces you can see spread across the two lateral force resisting system. Here it is lesser in this case. So to read these, you can utilize the section cut in the graphical window like this, and let's exclude only, sorry, exclude the frames and look at only the floors, then keep. So you can see the two 4700 in this case, in plane forces in the diaphragm. This is 3300. right? And yeah, these are the things I wanted to demonstrate. Let me also, yeah, under the outputs, for example, you can get the energy virtual work diagram that will give you from the linear cases, so which are the members that are having high work done directly in the graphical. The other one, which is called cumulative energy components, this is also available to give you. So we have involved the nonlinear analysis here, the pushover, and you can see the nonlinear historic damping from some of the members, and that energy component is being showed along with the potential. This is for 900 mm displacement, and you can see more energy and the damping. I mean, because historic damping of these frames and walls. I think you can also get a combined plot for decision making. And you can see this is pushover X, and then right now it is not accessible to me. It is on the top. So for each step, basically it gives you each step, and this is the envelope of all the steps. So if it is time history, then you'll get both left and right. This is a pushover, so one-sided envelope being recorded, and you'll get all the information. You can directly read these values for overturning moment, shear, drift, and displacements all in one place for this particular load case. All right. And that's it for today. That's what I want to give you a brief introduction on the features for a comprehensive code like this. There are a lot of things beyond this which cannot be discussed at this small session. So on your specific models that might be queries, please feel free to contact us through the support. We'll be happy to help you at any point of time. So thank you all.